Okay, here is the answer key for the Calculus 3 Practice Test 2. All these multiple choice we went through in class. I'm just going to briefly show the answers. That one's false. That is a true statement. It's the definition of the dot product that comes from. Two functions are not equal just because their gradients are equal. They could differ by a constant. That partial derivative is negative. That's impossible. That's false because the mixed second order partials would not be equal. fxy would not equal fyx. Both partials existing at particular points not enough to make the function differentiable. They have to also be continuous. That's positive. One goes up, the other should go up. Partial derivative is a directional derivative. Gradient is not perpendicular to graphs, ever. Ever, ever, ever. Gradient is perpendicular to level surfaces or contour lines. Same thing. And the gradient is not a directional derivative. Gradient's a vector. Directional derivative is a scalar. Okay, equation of this line. First thing we do is write this left side as some three variable function, some four-dimensional object with three independent variables. We take its gradient. That is a vector. Well, once we plug in this point, that's a function. Plug in the point, that's a vector that's perpendicular to this level surface. So, got that vector. Once we got the normal vector to the surface, the equation of the tangent plane, we just kept carry over A, B, and C, and we plug in our point, set that equal to 0. You can solve this, you can simplify it and get the constant to the other side. You can solve it for Z, whatever you want to do. This is the best version because there's no more work. Okay, we got all of our partials here. Just got to be careful. Partial f with respect to w is partial f with respect to x, partial w, partial f, partial y, partial w, plus. Don't forget to add those. And then we just need to evaluate. This is, what are our variables here? U and w. So we just evaluate everybody at 1, 1, and I got 4e squared. Check those details. Yeah, this one was long and nasty. You definitely want to check the details on this. I did not verify this. I mean, the process is right, but check the numbers. This is our formula for our quadratic Taylor polynomial, or second order Taylor. So we got to calculate all these partials at the point 1, 1. And then here's our linear approximation, this part right here. And then we add on all these quadratic terms. And here are all the things I got. Here's fxx at the point 1, 1. I got 6 plus e. fyy at the point 1, 1. I got 6e. The mixed partial at the point 1, 1. I got 6 plus 4e. So I've got 1, 2, and 2. And then just fill everything in. I am not simplifying that. I'm leaving that alone. You want to simplify that, you're going to be there all day. Leave that alone. Okay, next page. Okay, we did this one together in class, but to find all of our local extrema, we find the gradient, each first order partial, set that equal to 0, and then we solve this system of equations. I had to do a little bit of algebra here, and I got 2 points, 0, 0, negative 3, negative 3. Then I got to calculate the discriminant for both of those. So for 0, 0, I got 9. That's positive. Oh, no, that was only fxy. That's not the answer. I got negative 9. So that's a saddle point. If d is negative, it's a saddle point. And then for -3, -3, we get a positive number. I don't care what it is. It's positive. Got a positive number. fxx was negative at that point, so positive, negative, it's a local max. Okay, same game here. Only, whoa, this one is much longer. This was really long. Pause this. Okay, so we had to check all of our corners, our 3 points. We had to check our critical point, and then we have to evaluate the function for possible maxes and mins along each of these lines. So along the line x equals 0, I literally just went up here and plugged in x equals 0. I get this function of y. I take the derivative and set it equal to 0. That's y equals 0, so I get the point 0, 0. That's a new point that we didn't have before that I need to check. On the line y equals 2 down here, plug in y equals negative 2. Y equals negative 2 here. And I get this function of x, take its derivative, and set it equal to 0. I get x equals 1/2. So that was when y equals negative 2. So that's the point 1/2, negative 2. I think that one ends up being one of the winners. No, it doesn't. And then we need to check along this line right here, which is the line y equals negative 3x plus 1. So I take that expression, plug it in up here. I get all this stuff. I got to clean this up, take the derivative, set it equal to 0, and I get this weird funky x value. I need to find that y along this line, so I just plug that x back in here and find the y, and I get this point. That's another point I have to check. Okay. Now, I think, you guys check me on this. If I remember correctly, I Googled this problem after I had already written this up, and I think this may be wrong here. I think this one wins. I should just pause the video and go check, but you guys can do that. Plug this into Wolfram Alpha, and it'll tell you where the max or min is. If I remember correctly, Wolfram Alpha told me that this was the minimum value. I meant to go back and look for mistakes, but I'm not doing it now. So it's possible this guy was actually the min. So there may be something wrong with that. Plug in 1/2 comma 0 and see if you do get negative 0.25. If you don't, if that's a mistake, then this one is the minimum. But I don't remember. Check it and see. These two guys, I got 2 different maxes that were the same value. I got 8 for both of them. Okay, so check the details on this, but that's the process. Okay, this guy here, again, we kind of went over this one in class. We take each partial, set it equal to 0. We get, the only critical point we get is the point 0, 0. And our discriminant fails to give us any information there. We get 0. So really the way you would have to check this in the real world to figure out if this is a min or a max is plug in nearby values and see if you would have to plug in enough values to convince yourself that 0, 0 is always the smallest point locally or always the biggest point locally. Or if you plug in some values and z gets bigger and you plug in other points and z gets smaller, you might have a saddle point. And that's what's going on. If we let, here's our x and y coordinate system, as long as x and y are both positive or both negative, and we go out away from the origin, if we go out this way, either way, this function gets bigger. But if either one of them are negative, if we're in one of these 2 quadrants, the whole thing gets smaller if we move away from the origin. So the function's coming up here, and it's going down here. So this is a saddle point. And the only way you would actually be able to figure out it's a saddle point is plugging in a bunch of values, looking at the graph, something like that. So if this happens on the test, you would just say, we don't know. There's no info. Our second derivative test failed. Okay, we want the directional derivative. So we find the gradient, plug in our point, get a vector, take our vector, the direction vector, make him a unit vector, and dot those 2 together. And that's what I got. Okay, same kind of game here. Take each partial, set them equal to 0. We had to do a lot of algebra here. But solving that system of nonlinear equations, I get the 0.22. Here's all my algebra if you want to look through it. And then I find my mix, or all my second order partials and plug in x equals 2 and y equals 2. And I get a negative d value, which means that we have a saddle point. Okay, here's another one where the second derivative test fails. We're told that this is in fact a critical point. We do have to check that. So it does in fact make both first order partials 0. So that's a check mark. I said critical point. Yes, it is. Okay. We find all our second orders and they're all 0 at 0, 0. So we get d equals 0. We get no information at all. So the second derivative test failed. Okay. Oh my God, so many of these same questions over and over again. Using just the values we have here, we can calculate d, or discriminant, fxx, fyy minus fxy squared. We get a negative value, we get a saddle point, we're done. The maximum rate of change is the magnitude of the gradient at that point. So we find the gradient, plug in the point, that's a vector, take its magnitude, I got square root of 40. Okay, so we're taking the gradient. This question's a little misleading. We're taking the gradient because we need both partials. But we never actually needed the gradient as a vector. We just needed both partials. The differential, or the linear approximation, is right here. F at the point we're building this around, plus fx at that point times x minus a, plus fy at that point times y minus b, where this is the point a comma b. So we plug everything in, and I got this. And that's some number. So let me go back a little bit. Here's our linear approximation, our linearization. Now I want to plug in this point in there to try to approximate this value. That's x, that's y. All that really matters here is the change in x, which is 0.4. That's how far away that guy is from 1. And the change in y, negative 0.2, right there. Okay, and then just throw that in your calculator. You get whatever you get. We're on the last page. We're almost done. Oh my God, we still got like 17 pages left. Okay. The equation of the tangent plane at this particular point. So we take our gradient. That's the gradient. We plug in our point. I got, we need to first off, this is important, I need to make this a higher dimensional function. So f, capital F, is this thing minus z. Because this is z equals, right here, that thing there is z equals e to the x sine y. If I move z over, I get 0 equals that stuff. I get this, which is one particular level surface of this higher dimensional function. Now, once I have that, everything's easy because I just take the gradient. And so I take the gradient, I plug in my x and y. Well, what about your z? Well, in the gradient, it doesn't matter. The partial derivative with respect to z is just -1. I don't have to plug in a z value. But we may need it later. In fact, we do right there. So I went ahead and found the z value. There's our z naught right there. But it doesn't come in yet. Okay, here's my gradient vector. That's my a, b, and c for my normal vector. So I plug in my a. That's a 0. My b and my c. So there's no x. The x cancels out. There's my z value I needed right there. So here's the equation of my plane. Okay. Oh, I need to charge. Pause. Okay, so we are using the differential to approximate errors. So we find both partials. Remember the differential, dz is partial with respect to x, dx, plus partial with respect to y, dy. So we find both of those. I got 3 fifths and 4 fifths. I know my errors in x and y. That's my dx and dy. And then just throw this in a calculator, you get some decimal. Tangent plane, again, this is the same question over and over again. First thing we want to do is make this a higher dimensional function. So move the z over to the other side and call the whole thing capital F. Take the gradient, plug in your point, get your vector. You're going to need your z value from the original. So plug in your point, your x and your y to get the z, and then write out the equation of your plane. Okay, there, that one's really easy. Partial z, partial x. Look at that. This one's really easy. We went over it in class. It's just multiplying the right partials. F with respect to x, xr plus fy, yr. Okay, I can't, you guys can plug this stuff in calculators. I didn't type either of those into calculators, but this is what you should get. You can look through that, pause if you need to, see where everything goes. Here are all my mixed partials and so forth. Okay, directional derivative, find the gradient at the point, because we have a point, get a vector, dot that with a unit vector in this direction. Get your number. Remember, dot product is a scalar. And then this one was easy. Take the gradient, plug in your point, you get this vector. You're done. That's all we're looking for there. Okay, watch this. Good luck on the test tomorrow.